Today the topic is sensor technologies for urban monitoring. We will briefly introduce hyperspectral sensing. Then in the next presentation, we will talk about active sensor LiDAR, as well as 3D reconstruction using drone-based photogrammetry. This slide shows the photo of an ASD field spectral radiometer. It is an optical detector and a point-based measurement unit. The instrument collects spectral reflectance of radiation from visible near-infrared to short-wave infrared, approximately from 400 to 2500 nanometer at very fine spectral resolution. The white panel in the photo is called spectralon, which reflects 90 to 95% of the incoming solar radiation. The measured intensities are used to calibrate the reflectance of all wave bands. The figure at the bottom left shows the measured reflectance of a typical vegetated surface. The spectral resolution of ASD sensors at the visible near-infrared, the range is 3 nanometer, and it is 8 nanometer at short-wave infrared. Therefore, there are hundreds of measurements. The figure at the bottom right shows the sampled wavelength of multispectral Landsat missions. There are 6 bands from 400 to 1000 nanometer, 2 bands at short-wave infrared range, and 2 more at thermal infrared. This figure shows the spectral signatures of 3 land covers: vegetation, cloudinite, and silt loam. The curve or jointed dots show detailed spectral features appear as peaks and troughs. However, multispectral sensors like Landsat collect only sparsely sampled spectral measurement at several wavelengths, losing most of the necessary spectral information for separation of various land covers. Since every material has a characteristic spectrum based on the chemical composition of the material, it is possible to make use of the visible and infrared imagery for target discrimination. Whether the target is mineral, vegetation, man-made, or even the atmosphere itself, is based on the reflectance spectrum of the material of interest. Each satellite sensor is designed to record a specific portion of the electromagnetic spectrum. A major difference between multispectral and hyperspectral images is the number of bands within the same portion of the electromagnetic spectrum. The figure shows this difference. The number of multispectral bands on the top figure as compared to the number of hyperspectral bands in the same portion of the electromagnetic spectrum on the bottom figure. This table lists the differences between multispectral and hyperspectral imagery. In terms of number of bands, multispectral imagery typically has 5 to 12 bands. For hyperspectral imagery, it will have dozens and typically more than 100 bands. In terms of bandwidth or spectral resolution, multispectral imagery has between 50 to 2000 nanometers. For hyperspectral imagery, it is at much finer scale, from 1 to 50 nanometers. Since multispectral images only have sparse sampling in a few discrete bands, it has limited detection capabilities. In contrast, hyperspectral imagery have dozens to hundreds of continuous spectral sampling. The detection capabilities are much higher due to rich spectral information. The figures to the left shows an impression of a hyperspectral sensor with continuous sampling for 224 spectral bands within the wavelengths between 0.4 to 2.5 micron. The result is an image cube with a much more descriptive spectral signature very close to the field measurement of a spectral radiometer. An example of the spectral signature extracted from the hyperspectral imagery of cloudinite is given. The figure to the right is a comparison of the sampled spectral bands for multispectral mission of Landsat and Centennial and those for the hyperspectral mission Hemisphere. In the next few slides, we will take a brief look at the application of hyperspectral imagery. This is an example of mineral exploration. It shows an application of hyperspectral imagery for mapping polymetallic deposits in northwestern China. The mapped minerals include 7 specific classes. This is an example of oil slicks detection. The top figure in the left shows heavy oil slicks on the river colored in red, identified using hyperspectral images. The bottom figure in the left shows dispersed oil and polluted water appeared in black. The figure in the right shows that hyperspectral image can separate different percentages of oil mixes, which exhibit different spectral signatures. This slide shows the application of methane mapping using hyperspectral data cube. The example is a survey at a landfill using airborne hyperspectral sensing, with over 500 spectral bands measured at full stretch of optical wavelengths. The spectral features at short-wave infrared, over 200 nanometer, are shown to be useful for detection of methane. The methane concentration can be overlaid on high-definition airborne photos for easy spatial analysis. This example shows a typical application of species identification. The hyperspectral image is used to classify 5 types of trees. The 3D impression is created by the classification map draping over a 3D reconstruction created by LiDAR data. It is particularly useful for visualization. LiDAR sensing is a very important tool for climate modeling. It has been introduced and presented in other Moodle courses as well. We will briefly discuss LiDAR data in the next presentation. This example is getting closer to urban climate monitoring. The spectrally rich hyperspectral image is used to classify rooftop materials in building canopy. In Figure C, it is shown that false color composite using different fine spectral bands combination of hyperspectral data highlight the different materials, which is not possible with multispectral imagery, as shown in Figure A. Here we highlight some relationship between climate and urban cities. Firstly, the buildings and construction account for 37% of global emissions of greenhouse gases, which is contributing to global warming. The production and use of materials such as cement, steel, and aluminum have a significant footprint. Roofing materials plays a significant role in the overall environmental impact of a building. They can significantly impact energy consumption, water usage, and waste generation. By selecting the right materials, we can reduce energy consumption, conserve water resources, and minimize environmental pollution. A simple exercise of land cover classification using satellite images should have shown that it is very difficult to further classify subclasses in urban areas because of big variation in building materials. While remotely sensed data, such as satellite images, have been used to characterize urban land cover classes or to identify rooftop materials or raw materials. Since urban built-up materials are spectrally similar, it is challenging to separate, for example, asphalt-based roofs and roads, or specific urban materials and bare soil surfaces using multispectral imagery. It is especially difficult at coarse spectral resolution. Hyperspectral data are more effective and has been tested intensively for urban mapping. In the next few slides, we would like to showcase a milestone study in Hera's 2004 paper. It describes the use of a field spectral radiometer to build a spectral library for urban mapping. This slide describes the equipment for collecting field spectra. It uses the ASD field spectral radiometer introduced earlier in this presentation. All gathered data are resampled to a 1075 band spectra. The study area is at Santa Barbara, California. For the measurement, there are 108 targets representing 147 different and unique surfaces. Importantly, the spectra were convolved or resampled to 224 spectral bands so that they are comparable to the spectral configuration of AVIRIS, or Airborne Visible Infrared Imaging Spectrometer, a real hyperspectral imaging sensor. This slide shows a false color composite of AVIRIS image. It shows the location of 8 typical surface covers. The arrows represent the location of representative in situ measurement. These are the zoom-in of high-resolution image of 4 target urban surfaces. A. Red tile roof. B. Wood shingle roof. D. Concrete road. F. Parking lot. This slide shows 2 figures. To the left is the spectra of typical non-built-up surfaces, namely 1. Green residential grass. 2. Bare soil from construction site. 3. Bare soil from a beach. 4. Non-photosynthetic vegetation surface with landscaping bark. 5. Non-photosynthetic vegetation surface with pine needles. To the right is the spectra of typical road surfaces including 1. Asphalt road. 2. Concrete road. 3. Parking lot. And 4. Gravel road. The plot shows the potential for separating these urban classes with hyperspectral data, since they have more distinctive spectral signatures. Another 2 figures show spectra of typical roof materials for different colors and roofing materials. The purpose of this study is to infer potential of hyperspectral remote sensing for urban mapping, or rooftop materials and monitoring of aging and damaged road. Until recently, the availability of space-bound hyperspectral images acquired at full stretch 400 to 2,500 nanometers are scarce. But since 2019, the hyperspectral mission PRISMA from the Italian Space Agency and NMAP from the German Space Agency are offering global research communities 2 satellite hyperspectral data at 30-meter resolution. Both have more than 200 spectral bands, igniting momentum in all potential research domains. The bottom half of the slide lists many potential applications. Now returning to the possible application of hyperspectral remote sensing for urban climate mitigation. This slide revisits some of the contributors to high heat storage in the urban areas, which have been mentioned in the previous presentations. Urban building materials have high heat storage capacity, leading to higher surface and air temperatures. Urban canopies slow down the release of incoming energy. Hyperspectral data can be used to discern different rooftop materials, which could shed new insight to the relationship between building materials or rooftop materials and heat storage estimation. This slide shows the CURE urban heat storage monitoring application. It is extracted from the website of Copernicus for Urban Resilience in Europe, or CURE. It deploys various Earth observation and in situ urban data to monitor urban heat storage. The storage heat flux is defined as the net flow of heat stored within a volume that includes air, trees, buildings, and ground. CURE uses Copernicus services and satellite data for estimating the heat storage flux at the grid resolution of 100 by 100 meters, twice a day. The map values represent the rate of energy exchange between the atmosphere and the surface, with positive value indicating energy storage in urban surfaces, and negative value indicating energy release. For example, an area appearing with a value of 400 watts per meter square is storing energy at that time of satellite acquisition. Similarly, a value of minus 70 watts per meter square suggests energy release of 70 watts per meter square at the specific for the respective area. The figure above shows clusters of high heat release area at nighttime. As high heat storage is closely related to materials, hyperspectral analysis could upscale and improve the urban heat storage monitoring. This is an example of using hyperspectral remote sensing to define representative spectral signatures of urban materials. The first important category is roofs. Then, hyperspectral image can also be used to refine the characterization of impervious surfaces. The last figure to the right-hand side is the output of spectral unmixing method. It shows the estimation of pixel fraction of imperviousness, which is an important input for surface runoff model. The last example for hyperspectral images in urban climate mitigation is green space and tree species identification. We already discussed in the presentation about multi-scale urban climate predictor. Hyperspectral classification of tree species can be combined with 3D reconstruction from LiDAR data to project tree shades. Hyperspectral image is effective for detailed classification of vegetation and tree species. By fusing the species type derived from hyperspectral data with LiDAR data, we can have a better monitoring of urban greens and urban heat island effect. Here are some selected references used for this presentation.